much. My talk's going to be about work done by a recent thesis student, Ping Zhu, and a current thesis student, Nadia Drenska, who's right there. Most of you probably met her sometime in the last day. And, but I'm going to take a little moment to think back. Michael and I, well, let's see, George Papanikolaou was talking yesterday, and so he recalled this too. Michael and I met when he was working on nonlinear Schrodinger at Courant. I was an assistant professor. I was working with Yoshi Giga in those days. You heard from Pierre Raphael that nonlinear Schrodinger and parabolic blowup are very connected, and so we spent lots of time exchanging ideas. Then, of course, Michael moved on to Stanford, Princeton, Michigan. We weren't so much in touch. We read each other's papers. Then, fortunately, he came back to the East Coast, to the Northeast. I think from his perspective, the great thing about Bell Labs is the New York Marathon was right nearby. But it wasn't so bad that Courant was nearby, too. And so we reconnected. We did a few projects together. And I almost decided to talk about maybe one of those, but what I'm going to tell you today is current. It's also elementary, and so I chose that instead. I have a different relationship with Michael in one area. I bet I'm the only person who wrote a letter of recommendation for a co-op purchase, for an apartment purchase, for somebody in this room. You know, how do you write a letter like that? Well, of course, you put math in it. You impress the cooperative corporation. Okay, you can sort of guess what the letter said. The important point is they were approved. And also mention, I went looking around for a photo of Michael. I didn't have one, but I found one of my wife, Leslie, and his wife, Suzanne, having a lot of fun at a conference when we were listening to some talk that, as I recall, the talk was pretty good, but the robotics show was better. Okay, anyway, Michael, I want to express my own thanks, as many people have, for your leadership, impact, friendship, for the future years as well as the past years. Okay, mathematics. So I'm going to be talking about what in the machine learning literature is called prediction with expert advice. So this community would say they're doing prediction, but let's get this straight at the beginning, they're not using probability. So instead, the notion of prediction here, or the idea, the sort of paradigm, okay, prediction means there should be a data stream, right? There's a past, and there will be a future, and there's a present. So, and there has to be a notion of prediction, and the basic idea in replacing probability is that there are some experts. An expert might be very stupid. Lots of experts are very stupid, right? An expert might be very stupid, but an expert is an algorithm, in my case, a public algorithm for making a choice based on available information. And so you, the predictor, know what the experts would do in this circumstance, and you're supposed to make a choice. And you're going to compare yourself, after many steps, with the best performing expert. Okay, you know how the business news programs, sometimes they would invite a bunch of stock pickers. They would maybe have a computer choose stocks at random, and then they'd go back a couple of months later to see whether the computer did better. And so this is a bit like that. Back in 1965, Thomas Cover, the same one you might have heard of in terms of entropy and information theory, he actually worked in this area too. And one of the things he did was to say, well, look, let's think about this, a very simple model. Let's imagine a binomial process, a process of zeros and ones, or if you wish, plus and minus ones. We could think of that as a stock that goes up or down at every time step, but remember, no probability. There's no coin to flip. It's just the tree. And very simple model. Let's imagine that the investor, so we're thinking of this as a stock which goes up or down 1 unit in price. An investor who can buy or sell at any given time a fractional share of stock, at most 1. And then of course, if you buy stock and the value goes up, you gain. As you sell and the value goes up, you've lost, and so on. and I'm going to discuss there could be more experts. I'll get to that at the end, but I'm going to emphasize the case with 2 experts. You'll see that that plays a significant role, and so, okay, this notion of regret, that just means you compare yourself to any particular expert, and you either have a shortfall or a gain relative to that expert, right? And so in this literature, the typical goal, I already mentioned it, is to compare yourself to the best performing expert. Okay, but what are you going to assume about the market? Well, since there's no probability, it's not your expected outcome, it's your worst case outcome. You're going to suppose, as we often do with the stock market, that no matter what we choose, it knows what's worst for us, and it's going to do what's worst for us. So that's the model here. So you're trying to optimize under the assumption that the market will work against you, your outcome at a given future time t. And that worst case value is really a rather special case. As you'll see, the ideas I'm going to describe to you, well, at that fixed future time, you can calculate how you did relative to expert 1 and how you did relative to expert 2. And in fact, your way of assessing what you would like to achieve doesn't have to be the max of those 2. It could be any function of those 2 variables. Okay, so let's see. The top of this frame is just to remind you where we are, the tree and the 2 experts and the choices. I didn't tell you about the 2 experts. So for quite a while in this talk, I'll talk about the 2 very simplest imaginable experts. These are very stupid experts. One always thinks the stock's going up. The other one always thinks the stock's going down. So the optimistic one chooses to buy, of course, the maximum possible. The pessimistic one chooses to sell the maximum possible. And after we've understood that, we'll step back and ask, okay, now a more realistic expert might make choices depending on history. So what about that? So the simplest experts, that's thesis work of Kangping Zhu. And the more realistic experts, that's not just thesis work. My basic viewpoint is that this is really an optimal control problem. I'm going to use dynamic programming. So optimal control problem, so what's the state space? The state space, the space in which the whole story is sort of Markovian, except there's no probability, is the plane. Since there are only 2 experts, it's a 2-dimensional plane. We look at the investor considers his shortfall or regret relative to each of the experts. And so here as a picture, I said, well, I mean, if his outcome is the maximum, whichever of those is larger, then of course what I've drawn is the set of equal value outcomes. And the optimal control problem, you need a state space, you need a control. This is the investor's optimal control problem. He's making a stock purchase or sale. And the investor's value function, well, that's what we're trying to optimize. So the value function is assuming that the market will work against him, it's the optimal final time result. That is to say, the optimal value of my preferred function phi evaluated at the final time state. Okay, so dynamic programming, that's pretty simple. The general principle is that we think one step at a time. So the value function starting at any particular point in regret space at time t, well, the investor is choosing his investment. He's doing a waste case analysis, so considering that the market might go up or down at the next time, and whether the market goes up or down, and depending on what investment he made, he'll go to a new point in regret space. And the dynamic programming principle says that you should make his decision so that he achieves this, that the value today is the best I can do amongst my investors' choices, the worst that might happen amongst the market's possibilities of the value tomorrow at tomorrow's position. Of course, this is a final time problem. The final time is where my objective comes in. And then there's a little algebra, of course. The question of the rules of this game determine the new position in terms of the final position. I wrote down the formula there. We'll go over it in a moment, but that's just algebra. Okay, that algebra, this is just to be sure you know that I'm not cheating. So we're studying regret with respect to the first expert and regret with respect to the second expert. The regret is the shortfall relative to that expert. If the investor bought a fixed number of shares, market goes up, the investor gains according to his number of shares. The optimistic expert bought a whole share, and the negative expert, well, market went up, negative expert sold, so he has a loss, and so the state moves, so on. And the only important point here is that the move is linear in F, the investor's purchase. Okay, so that's how I got my dynamic programming principle. Now, actually, I'm not quite going to use that principle. If in this setting, of course, you're not interested, there's nothing to say about one time step. You're interested in many time steps. It's a situation very similar to what we do in studying random walks, and we know very well that sort of appropriately scaling a random walk, we get Brownian motion. We can study Brownian motion by studying PDEs. And what I'm going to do here is something very similar. I'm going to take a continuum limit, a limit that's appropriate, that's the direct analog. There's no probability, so it's not quite the same as we do when we get Brownian motion from a random walk, but the scaling, the sort of method of getting from discrete to continuum, that's the same. Okay, so my scaled version of the problem, I'll consider the stock moves to be plus and minus epsilon time steps. You'll see y are of order epsilon squared. And otherwise, I keep everything the same. The value function is still the optimal worst case, some fixed future time result. And so the principle of dynamic programming, it changes only because since the stock only went up or down by order epsilon, this linear law that I wrote before requires a factor of epsilon. And what we expect is that in some limit as epsilon goes to 0, we're getting a PDE. So how do you find the PDE? And the answer, if you've ever studied dynamic programming, maybe you read Craig Evans' book about the relationship between optimal control and Hamilton-Jacobi equations. If you've ever studied this subject, you know that the basic principle is solutions might not be smooth, you don't know, but never mind that. Cheat wildly by Taylor expansion, and then worry about proving it afterwards. So we proceed to cheat wildly, and if I expect the value function that I got at stage epsilon to be converging to some limit. So let's even drop the subscript and pretend that W is independent of epsilon, and then we can use Taylor expansion to understand what's happening at the next step. And the basic principle is that the investor will choose his investment F so as to zero out the leading order terms in Taylor expansion, and we're going to get a PDE at second order. And I'm going to spell that out in a minute. And the PDE it's not the heat equation, but it is parabolic. It's a little nonlinear. If you've ever studied motion by curvature, you might recognize that its similarities. And okay, but somehow the idea is more important than the equation right now. So let's go to a more developed version of that idea. So what I told you, so the principle of dynamic programming is at the top. And when I use Taylor expansion, treating epsilon as a small parameter, well, I'm going to keep both first and second order terms. Of course, there are higher order terms, and I didn't write them down. Now remember, what I was trying to do within that Taylor expansion is to do a max min and canceling W of position x and time t appears here. In the Taylor expansion, it's the first term. Zero that out, and then my principle of dynamic programming looks like what I wrote here. And since the steps are linear in F, and the leading order term is linear in the first derivatives of W, and so there's a choice of F which makes that leading order term vanish. And if it didn't vanish, then choosing whichever sign is worst, this min would be non-zero. It would dominate. Essentially, if the investor doesn't make these leading order terms vanish, then the market will make a choice that kills him. So he has to do that. And making that leading order term vanish, it means the investor makes himself indifferent at some leading order way to whether the market goes up or down. Then we go to the next term, and the next term, F was determined by zeroing out the first term, so you do some substitutions, and you get an expression involving first and second derivatives, and that's the equation I wrote down. And the condition that the first order term vanish, it gives you F as some expression in terms of first derivatives. Okay. So that's the PDE. Now there's some happy accidents. One happy accident is that this PDE has a very simple geometric interpretation. So this is an evolution equation in two space dimensions and one time dimension. If I draw the set W equals constant, it's a curve which is moving in space. Its curve moves in two space dimensions. And the fact is that skip the algebra, don't think so much. They'll save your mental energy for later. But with a small calculation, that curve moves by a geometric law. Its normal velocity in the plane is twice its curvature divided by a number that depends on its normal direction. Okay, so it's not just it's a very nonlinear equation, but it's not a completely arbitrary equation. Actually, there's even a greater miracle. Yoshi Giga was visiting New York when Kang Ping and I had first sort of been about this stage, and he said, "Oh, your equation is the world's most complicated way to write the linear heat equation." And one way to see that is you introduce rotated coordinates in the plane, and this level set of W equals constant, you try to write it as a graph over the xi axis. So that means eta is a function of xi and time. And you do some algebra and you discover that's the linear heat equation. I'm doing final value problems, so of course it's the linear heat equation with a plus sign in front of the Laplacian. And of course, that's nice because it means that we understand everything about this equation. It means that unlike Hamilton-Jacobi equations, there's no singularity development. Okay. I told you that the right thing to do in a problem like this is you do Taylor expansions even though you weren't sure it's right. And then you worry about fixing it later. There are two approaches to fixing it. One is to rest upon viscosity theory, which works even when the underlying equation solutions are singular. But there's an older way. It goes by the name verification argument. Very closely related to the method of characteristics. And since our solutions are smooth, we worked out a proof that way. The theorem says that W epsilon, the honest value function for the game, for the investors' competition against the market when the scale size is epsilon, that it agrees with the solution of the PDE with an error of order epsilon. I'm lying slightly. That's the statement when your way of assessing how you did at the very end is smooth. And if instead your way of assessing how you did at the very end is you just compare yourself with the best performing investor, well, then this estimate isn't quite true because, of course, Taylor expansion is contaminated by the singularity from the max function, and so there's the theorem has an extra logarithm there. Okay, how do you prove this kind of a thing? Well, it's really two inequalities, as I wrote. You have to prove that W epsilon is less than or equal to what the PDE analysis would tell you, but not but also very close on the other side. And these arguments are essentially associated. One says, well, the investor has instructions from the PDE. So following those instructions, it might not be the best policy. You have to prove it, but at least it's one policy. What does that give? And then there's the other argument, which you have to consider, why is that the best policy? Let me just give you the spirit of how this kind of thing goes. So we'll prove one inequality, and we'll do it by using the fact that the PDE gives us a suggestion what to do. So that means we have to estimate W epsilon at an arbitrary point. And the basic idea is no matter, so at some initial point in Z naught is like x, it's a point in the plane which represents shall we think of it as today's location in regret space, and T naught is today's time. So we'll find a sequence that moves in time to the final time and moves appropriately in space. And on that sequence, the solution of the PDE will be nearly constant. And by the way I choose the sequence, the W epsilons will be monotone. And if you can do that, well, then, of course, there's one more thing. Both the discrete process and the PDE have the same final time data. So then from such an arrangement, if I have one of them is essentially equal and the other one is essentially monotone, they agree at the final time, then they have an inequality at the initial time. Okay, where's that supposed to come from? Well, remember we had a dynamic programming principle, and the PDE has told us how to choose F. Okay, so if we consider the position, if we consider that as the only move we're going to consider, then the investor's value function, well, it's a min, it's the best policy. We don't know if that's the best policy. It's less than or equal to the worst that the market will feed you using that policy. Okay, and since we don't know whether it's optimal or not, we suppose that this max that the market gives you there might not be complete indifference. And okay, but whatever the market chooses, we can choose that for the next step in the sequence. So by this method, we guarantee that W epsilon is monotone along this sequence. And as for the PDE, well, remember where it came from. The PDE had exactly the feature that when I follow the policy associated with the PDE, the first order terms vanish. The second order terms, well, I set them equal to 0. That was the PDE. And so there's only the Taylor expansion remainder. So it means for the PDE along the sequence we just discussed, it's monotone up to an error of order epsilon cubed. So time steps by order epsilon squared, and therefore the errors accumulate, but only to something of order epsilon. So that's the idea of the convergence argument. Okay, I made you work a little bit. Maybe you're tired. It's the middle of the afternoon. Don't worry. So the work we just went through, it doesn't matter whether you followed it because we're going back to more or less formal level now. The story I told you was about those two extremely simple experts where one always is an inveterate optimist. He buys stock every day. And the other one is a complete pessimist. He sells stock every day. And now we want to ask, well, yeah, okay, but a real expert might easily be sensitive to history. So this is Nadia's work now. Two history-dependent experts. So what might that mean? Let's keep a fixed number of days of history, maybe D days. And, well, I mean, if I decide to record ups and downs as a binary digit, then I could, each possible history is expressed by D binary digits. And let's just suppose that each expert makes a choice that is some publicly known function of history. Now, you might say, oh, what about experts that change their choices as history goes on? Well, if they don't look back infinitely amount, then that's still a function of history. What about experts that somehow change their minds? Or maybe random or something. Well, the ideas I'm going to tell you certainly generalize, but let's stick, now this is already, I think, a reasonable framework that the expert thinks about the last 100 days. Otherwise, everything's the same. The goal is to optimize the worst case final time value of regret using either by comparing yourself to the best performing expert or by evaluating some other function of your shortfall relative or regret relative to each expert. And now I can't call my experts plus or minus, so I'll call them Q and R. Q and R are simply the mappings that take you from histories to take the experts from histories to choices. Okay, so, well, dynamic programming was pretty successful. Let's try again. And, but then you realize it gets a little messy. I mean, you can certainly formulate dynamic programming, but you seem to need, but now the value function is certainly a function of the state as well as your point in regret space of a continuous variable and a discrete variable. And there's a lot of states. And then you think a little more, and you realize that, well, maybe that's not the right viewpoint, because the stuff that was driving the previous calculation was that second order in Taylor expansion. Somehow the first order term in Taylor expansion got zeroed out. So regret accumulates slowly, while the states are changing every moment. So you might expect that there's a sort of a fast variable, slow variable structure here in which the changing of the states is the fast variable, the accumulation of regret is the slow variable, and you should think about them separately, not together. And, but we still think that, I mean, we still expect that the investor should choose what he does to achieve some kind of leading order indifference to whether the market goes up or down. And I already said that regret accumulates slowly. Okay, so let me show you how that leads, that set of ideas leads to a PDE. Formally, this is back to my cheating wildly mode. So, of course, we're still in regret space, a two-dimensional regret space, regret relative to the Q expert and the R expert. And the investor's going to make a choice, and then the market's going to up or down, and each regret is going to change by an amount that's linear in the investor's choice F. Of course, depends. It's the same formula I had before, except now Q of M isn't +1 and R of M isn't -1. And so market indifference, that's easy. Market indifference still tells me there's a unique choice of F that makes this equal that. No, I didn't say this equal that. That makes the leading order term in Taylor expansion vanish. If I expand my value function in Taylor expansion, and therefore I can see how much it changed, it's an expression that's linear in the first derivatives of W, linear in F, and there's one expression when the market goes up and another expression when the market goes down, and of course now the selection of F that is needed for market indifference, it depends on the state. But except for being dependent on the state, it's the same calculation as before. And then we can go to order epsilon squared in Taylor expansion. This argument told us what the investor should do. And at the next order in Taylor expansion, this is the expression that we had before, except where we used to have a constant, now we have a coefficient that depends on the state and depends on the difference between what the Q expert and the R expert did. Makes sense. You don't accumulate any regret if the two experts did the same thing, because then you would have done the same thing as they would have done. Okay. And the worst case scenario, well, it's the one that accumulates regret fastest. Okay. So this expression, this is how the sort of slow evolution depends on the state. So that's the fast variable. And okay, so now we have to ask a question we didn't ask before, which is, which market scenarios are the worst I can imagine? And the answer is, well, if we remember that the fast variable, the market, is this Q minus R, which will change from state to state. But the slow variable, let's hold that frozen. So all the first and second derivatives of W, they're frozen. And so this expression here, it's just some number. And then I'm left with a problem in graph theory. This is just a number, so I can ignore it. I'm asking, well, as I go over many time periods, what's the worst case accumulation of this coefficient Q of M minus R of M squared? And now you realize that in the space of possible states, from any state, the market could go up or down. So there are many states. Here I drew the case of keeping only 2 days history, and therefore it has only 4 possible states. Keep D days, you would have 2 to the D states. But from any state, there's only 2 possible states you can go to. The one where the market went up and the other where the market went down. Okay, so there's a graph, and you could think of each leg of the graph, each link in the graph, as having a value, a sort of call that cost, and the value is Q of M minus R of M for the M from which that link starts. And so we're asking, as you imagine different ways of moving on this graph, what's the worst case accumulation of this sum? So this is the study of the fast variable, if you wish. And okay, a little lemma that's enough to study cycles, and there are good algorithms for finding optimal cycles. This goes to some classic work by Karp in the computer science or graph theory literature. So that's the answer. So the answer finally is it's a PDE that's essentially the same as we found before, except what used to be a sort of a diffusion constant that we found without even thinking about it becomes a constant that we have to find by this calculation about the graph. Okay, now I told you that the name of the game is you cheat wildly and then you prove your cheat was okay. Here too, the correctness of this equation, a convergence theorem similar to what I described before, can be proved. The argument's a little more complicated because you have this fast variable, slow variable separation. We still use a verification argument, and I'm not going to try to show you that. Instead, in 4 minutes that's left, let's sort of step back a little bit. Okay, a very natural question is, well, if this whole picture is limited to two experts, that's a little sad. I mean, that's very special. And so what about more experts? From our viewpoint, if there are more experts, then you're moving in a regret space that has the dimensionality of the number of experts. Okay, so if I can do this picture, then I'm going to get a PDE in many variables. That's also a little sad because we know that PDEs are hard to solve in many variables, but that's life, it seems, so far. And what we expect is that the overall framework would be much the same. The investor's choice would be set by market indifference at leading order, that you would have to do some kind of a calculation on the graph to find out what's the worst case thing about the market that you should think about. But the difference will be that where previously this calculation, involved a single scalar, in higher dimensions, you're not going to have such a clean separation. That you're going to get a much more nonlinear equation, that there will be regions, that depending on the value of the second derivatives and first derivatives, you will have regret that accumulates in a way that has more complicated dependence and therefore will be probably not reducible to any familiar linear equation and a more complicated nonlinear equation. And so, well, that's what Nadia's doing now. Mathematical messages. The bottom line message is the literature in this area is almost entirely discrete. There's a lot of literature. I didn't give you a proper review of the literature, but there's a lot of literature. It's almost entirely discrete. Our real starting point success was to ask, oh, well, in a lot of other discrete problems, when we're interested in the net effect of many time steps, we study continuous limits. Isn't that a good idea here? The math underneath what I've told you here, the PDE, the verification argument, and so on, actually, it's very closely connected to things I did some years ago with Silvio Serfati. In fact, I came to this problem because one day I received a phone call from somebody from Microsoft named Rina Panigrahi. He said, I'm working on prediction, and a friend of mine said I should talk to you. And the reason, I'm sure, is that his friend knew my work with Silvio. Comparison to the mean, let's see, I said some of this. I didn't say that, okay, so the gentleman who talked to me, collaborator is Andrea Andoni. They've worked on the simple experts version of everything I got to before I started history-dependent experts. The difference between what they did and what we did, essentially, we found similar strategies, essentially the same strategies. I mean, here I've given you a way to prove that they're optimal. They didn't have that tool, but they understood a lot. Then there's the question of, is this approach to prediction a good idea? If you, okay, I would tell it to one of my finance world friends, and he would say, are you kidding? What's the stuff about thinking about worst case scenarios, right? If an insurance company never wrote a policy if there wasn't the possibility that they could go bankrupt, they wouldn't do anything, right? They think about probabilities of failure, right? So, and the answer, I mean, okay, a machine learning expert's answer to that question is, oh, well, you should have many experts, but not too many. And so there's some, or sometimes they'll say, oh, but look at the great things I can do with methods like this, right? And so I don't have a general answer to that question. Anyway, more generally, so I have the suspicion that continuous thinking should have more than just this use in thinking about prediction, but that's really conjecture. I'm going to stop there, except, again, to wish Michael a happy birthday.
Any questions for Bob?
So as you're saying, your model is based on the notion of risk minimization. Is there a companion model that might be called, maximization of ego, which is to sort of do better, and then you could introduce a notion of risk tolerance as a trade-off between the two cases?
Yeah, so good question, and I don't know such a theory. I can't say it isn't there because it's a big area that I don't fully know it. So it's a good question.
Would you care to say anything about the work in progress? Do you expect to get a PDE or a free boundary problem?
Okay, so we expect to get a nonlinear PDE where WT plus some function of second derivatives and first derivatives equals 0. And the thing is that it's going to be a more complicated function. Maybe there will be free boundaries, and within some regions there will be simpler stories, but it'll change from region to region. Don't know. And without the sort of, if the solutions turn out not to be smooth, which in a regime change situation you might expect, then maybe viscosity methods will be needed instead of verification arguments. That's sort of a big picture sense of what we expect.
I'm just going to go here.
Yeah, there's a notion called the wisdom of crowds. So is there something like the limit of an infinite number of experts that might lead to simplifications?
I think, so this goes into the, at some level you're asking, is there some relationship between this and trying to extract information from a community by betting, crowdsourcing, right? And I don't know. Good question.
I have a question.
Yes.
Is the limit problem the HJB equation of something?
Okay. So I would, in some moral sense, so I describe this as an optimal control problem, but really it's a two-person game, right? There's the investor and the market. And if you think of it as a game, then at some level, the PDE is the Hamilton-Jacobi-Bellman equation of that game. Except, of course, that the game is discrete, and you get the PDE only in the continuum limit.
The question is, does there exist a, can you describe the limit, the PDE, the nonlinear PDE?
Okay.
as
I'll
a-
fall back on the following. Okay. So I mentioned my work with Silvia Serfatia, sort of the similar mathematical tools. Our first application, Silvia and me, was to give a two-person game dynamic programming interpretation of motion by curvature. Now, in that setting, the answer to your question exists, and that's that if you go probabilistic, and the market is, so everything's continuous time, but the market is choosing between different Markov processes in continuous time. So then there's a completely sort of continuous in time optimal control interpretation, which needs no discretization. And it was worked out by Buckton, Cardiel-Laguet, and Quincampoix, and generalized by Tuzzi and a bunch of others.
So your equation for W towards the end had this, you had this separate, by using scale separation, you had computation of what looked like an effective diffusion constant.
Right, right.
And so are there any connections with homogenization, and could you have guessed that diffusion constant and whatever emerging time scale without going through the whole calculation?
So I mean, so this is like time homogeneous. It's like method of averaging, if you wish. Right. And the calculation resembles very much the method of averaging. At some level, that's what we're doing in the graph. But I don't know any sort of other way of thinking of it that makes it easier. Oh, if the experts choose randomly, replace the graph calculation by the expected value of Q minus M squared. Right. So that's, again, closer to the method of averaging. Right.
More questions for Bob? If not, we can thank him. And we'll continue at 4:10.